Hello guys, welcome back to the stream. So today what I'll be doing is writing tests as I promised to do on Sunday, but I was a bit off, so I took a day off. Now let's write some tests. Starting with I'll write some unit tests first to test specific behaviors. Starting with the Snowflake ID generator and in the internal, I will write test for retry engine. After writing these tests, I'll think of what other things I need to test and all later. But for today, my goal is writing test for the Snowflake generator and for our retry engine. The part of the GoTaskQ where I am converting the GoTaskQ into library is postponed to some extent until all tests are written. I'll write tests till then, and after that, I'll implement the library function. After that, we'll see what needs to be done and all that. So let's get started with the Snowflake generator. So what the Snowflake generator does is, let me give you a recap. It generates Snowflake IDs based on sequence bits, machine ID, and maximum. So what it does is, when I create a new Snowflake generator, it takes a machine ID and gives me back a Snowflake ID generator. So it has various methods. Mainly, it has one method mainly, which is next ID, which tells us what will be our next ID. So next ID takes current time. Based on that, it does processing. It tolerates some drift up to 5 milliseconds. It also can generate 1024 different IDs for the same millisecond by using the sequence bits. And I think it's all we need to think about. Uh, let's start writing some tests. First test will be trivial, which will be small. Writing the test for the new functionality. Let me just write a new Snowflake uh, Snowflake underscore test dot go. Writing tests in Go is pretty good, you know. You don't need any additional framework to write normal tests. And the test environment is still pretty good even with only local only language libraries. So let's write a function func which will test new. Let me import it, and this we go. Okay, so test new, what will it do is it will check, firstly it will check if the machine ID passed is valid. And if the machine ID is invalid, we have two cases: if the machine ID is negative or the machine ID is greater than max machine ID. So let's do it. Max machine ID is already set, which is 1023 here, because we use some bit shift mathematics, and that gave us 1023 as the um, upper limit and 0 as the lower limit. So any machine ID which is less than 0 or greater than 1023 will be our what we call invalid ID. So let's test this. So first thing I'll test is the happy path, which is if a valid ID is passed, we expect what. Then let's test it. T.run. I'll have subtests. I'll have three subtests. First will be happy path, which will be our um, valid machine IDs. Okay. So for valid machine IDs, let's me write the test. It will have a function, and for this function, what I'll do is I'll have a let's have an array of integers, which has like say four values 0, 1, 5 and 12 and 10, 23 to test different values. Let me write that tests equal to int64. As you remember, the ID is int64, so I'll be taking this, and the tests will be 0, 1, 5 and 12 and 10, 23, which is our upper bound, 0 is our lower bound, and two IDs in between. I'll range over these IDs. And then I'll check if the uh, Snowflake generator generated by this is with the correct ID. It's trivial, but let it be. Or underscore ID, write it faster in our range of tests. What I'll do is I'll have um, a new generator with our ID, ID, and if s dot machine ID is not equals to ID, then we will say expected ID to be this, and got that p dot error f, and expected machine. So error f, what it doing is machine ID as %d dot %d, and our ID will be s dot machine ID, and sorry, it will be ID and s dot machine ID. Right, the test for happy path is done. One test is for invalid ID, negative invalid IDs, or I can simply say invalid IDs. P dot run. Let me name. Oh, sorry. Press the wrong. Invalid valid machine IDs. So I'm thinking invalid machine IDs. Machine ID. And let me write it negative. What we are talking about is negative machine ID. And the function will be like this. What we'll do is we'll simply use the defer func to call this. What I'm doing in defer is I'll recover from the panic. As you can see, if there is invalid machine ID, it panics with invalid machine ID. So what I will do is if R is to recover from our what we'll do is recover. Okay, we'll take this as recover. R, if R equals to nil, it means it did not recover. It did not need to recover. So it means there was no panic. So what I'll do is expected panic or negative IDs. Okay, I can say negative IDs. So what I'll do is I'll simply call what we call it new with -1. So what will happen is we'll call new with -1, we will get a panic, and the defer function will be invoked, which will recover the panic. And if recover is not called, it means we didn't get the panic, and the function succeeded even with negative value. So last thing we need to test in this is t.run invalid machine IDs, invalid machine ID, um, larger, uh, bigger, bigger, bigger. Okay, bigger is enough. And what function will be like this? Just copy this from above, paste it here, and use instead of -1, I'll use 1024. I could have done this like in a loop or something, but it's okay. It's only two cases, so uh, that's okay. I can simply run the test from here. So let me run the test, and it got okay report. Um, so I think new function is valid. Next thing is our next thing we'll do is check our main function, which is next ID function. So fun test next ID. So what next ID do is it generates new IDs. So for that, I'll have a generator with the sorry new subject one. Okay. Now I have a generator with machine ID one. So first thing we'll check is if the IDs generated are positive and increasing, because as you know, um, Snowflake IDs are time based. So time always increases monotonically. So we'll check if the IDs also increase monotonically and should be positive. They should never be negative. So two cases we will test first. So it's right t.run. What we are testing is monotonicity. So what I'll write is function. Oh, sorry, function, and first thing we'll generate two IDs. Next, s dot next ID, and call it ID one. One more ID will generate it. What is this? Why is my tab not working? Sorry. ID two s dot next ID. We are generating two IDs, right? So first we'll check is if ID is negative. So if ID 1 is less than equal to 0, or ID 2 is less than equal to 0. If either of those IDs is negative or 0, we will generate error. P dot error f. The error will be ID should be positive. Should be positive. Got %d and our ID uh, and ID 1, ID 2. Okay. Then the next thing we'll check is monotonicity. It means it is increasing monotonically. So let's test it. If ID 1 uh, is, is greater than equal to, which is wrong case, because ID 1 should be always smaller than ID 2, because ID 1 was generated first. So what we'll check is t dot error f IDs should be monotonically increasing. and let's say %d smaller than equal to %g. Uh, as long id2 smaller than equals to id1. So the programmer can debug easily. Next thing we need is um, to check the sequence overflow thing. So what Snowflake ID does is, if the sequence gets overflown, it means it can generate up to sequence number of IDs in 1 millisecond. If a sequence get overflow, it waits for the next millisecond and then generate IDs. So what I'll do is, uh, I'll test it using for this thing specifically. I think we will need a time function manipulator, because time here, if I simply call this twice in a loop, it will take different times. So we need to have current millisecond value to a specific value we want, so that we can check the sequence. For that, I think I should I'll expose a hook. So time hook for current millisecond for testing purpose. It will be a global hook, package-based global hook. What I will do is, I'll have a function let's say now millisecond, which will be equal to a function which gives us int 64, int 64, and one thing I forgot is brackets. It will give us int 64, and it will return us time dot now dot unix milli, as we used in our current millisecond function. So what I'll do is, I'll use uh, now milli here instead. Now milli is invocation in the current milli. So whenever wait next millisecond, which calls current millisecond, I can simply change this function's behavior in our test, and set a particularly static time. So let's back up the. So let's write the test first. T.run. I'll have a test which will be uh, for sequence overflow. Okay, it will be a function. So what I'll do is, I'll back up the original function. Original now milli. So I'll back it up in this variable. So it is a function that returns int 64, and it contains the value of now milli. Okay, so I'll have a cleanup function, t.cleanup, which will simply do is set back the now milli to original now milli, so that runtime does not get affected by the test. So let's have a fake time. Fake now equals to, we need a int 64 Unix milli string. I have one. Let me write it. Int 64 conversion of 171112. Let me copy paste it from one of my references. Okay, so I have this. So it will act as our static time. Every call will be made in this millisecond. So let's do one thing. We'll check the number of calls made. Okay. And now we'll update the function. Now Milli function will be updated in this part, which will be I will update func 864. What it will return is what it will do is it will increase the number of calls plus plus. After that, if I'll have a cap at calls, because what I'll do is I'll test the behavior when sequence is one less than the max sequence. So the max sequence is our uh, uh, here we have max sequence as where is it? Let me just check it out what our max sequence is. So I'll have it one less than this. So 4095 is a max sequence value. So what I'll do is I'll have it one less than that. So it will be 4094. Current sequence will be 4094. So for overflow I need to make two calls. So if calls is greater than equal to 2. If false is greater than equal to 2, uh, sorry, if false is less than equal to 2, what I will do is I'll return fake now. But if it is not, I'll return fake now plus 1. So you might be thinking why I return plus 1. So plus 1 is returned because in wait next millisecond, what I was doing is I was waiting for 1 millisecond. So for plus 1, that's why I did plus 1. Okay. And so now let's write the function. We have a new. I think I have yeah, I have defined it here. Okay. And that is fine. So I'll set up s dot last stamp, which will is last timestamp equals to fake now. No name s dot last stamp on the left side of the compiler. I think I should define it there. New s equals to new with ID one. S dot last stamp. Non-name s dot last stamp on left side of compiler. What does it mean? Oh, one thing it means. This is not the issue. I was reusing that. Okay, s dot sequence equals to as I said, max sequence minus 1. So there will be only 2 sequence for us. Check. So first thing I will do is ID 1. I'll generate ID with s dot next ID, and this will make the sequence increase by 1. So increase sequence will be equal to max sequence. We will check if s dot sequence is not equals to max sequence. That means we got an error. So we will have t dot total f expected sequence to reach next sequence next sequence dot percent d will print out the sequence value currently we have f dot sequence, so we can debug. Okay, I have id generated. And I'll now generate one more ID, ID2, which will be s dot next ID. In the same millisecond, first thing we will check is ID2 is less than equal to ID1. That means uh, we expected ID to advance after sequence overflow. Expected ID to advance after sequence overflow. All right, let's give percent d less than equal to percent d, and that will be ID2, ID1. All right. One more thing we need to check is when sequence reaches max sequence, we set the sequence equals to 0 here. Uh, yep, here s dot sequence equals to end of this. So this will be set to 0. So if sequence is not equal to 0, if it is not equal to 0, we will have error. Expected sequence to expected sequence to wrap to 0 after overflow. We got percent d. The percent d will be our s dot sequence. And last thing we need to check is the timestamp. If s dot last stamp is not equals to fake now plus 1, this will check if the time has been increased, which we increased here. If it has been increased, then that means our function ran successfully. If it is not, that means there was some issue. So what I'll do is t dot error f. I'll have expected last stamp to advance, to increase after overflow. You got percent d s dot sequence, and that's all the errors we need to test. We can also run next ID, but one more thing we need to test in next ID is concurrency safety. Because we are calling the next ID function using goroutines. The goroutines can run simultaneously, so we need to check for concurrency safety. So what I'll do is I'll spawn goroutines with the wait groups, and then I'll check if there are duplicate ID generated or not. If there are duplicate ID generated, it means our Snowflake ID generator is not working good. And if no duplicate ID generated, then that's all right. So let's write a test. T.run concurrency safety. You need to check if this package we created is safe in concurrent environments. So what I'll do is I'll create a new machine. No need to create a new machine, I think. I'll have a wait group. sync dot wait group. I'll have a wait group that will check the number of I'll have num go routines. Number of go routines. Let's get them to 10, and each go routine will call around 1000 IDs. IDs per go routine. Okay. Those 1000 IDs will be checked by will be generated by each go routine. So what I'll do is I'll create a buffered channel chain where the go routines will store their IDs. Okay, so let's do it. Make our type will be channel of int64 as the ID generated is int64, and the value will be num go routines into number IDs per go routine. So that will be 10,000 in this case. So there will be 10,000. The channel will be buffered for 10,000 responses. So for each go routine, num go routines, I'll do is wait group dot go. So this function particularly does is it adds a wait group, and when the function returns, it subtracts the wait group internally. So I don't have to add and subtract like that. One, I'll have a function for the range of IDs per go routine. I'll have in ID chain, I'll write in ID chain s dot next ID. Okay, so it will store all the IDs generated. Now let's wait for our wait group to finish. Wait group dot wait and close the channel. Okay, the channel has been closed. Now what we'll do is we'll check. We will have a map to store all the IDs one by one, and if any ID repeat, there we will throw any error. Map of type int64 64 and 2. Okay, so we will iterate over our ID chain for ID in our range of ID chain. What we will have is, if simple logic, if we have seen the ID, then we will throw error p dot error f, which will be duplicate ID generator in concurrent environment. ID generated in concurrent environment. Okay, and %d will be the ID. Okay, if not, then we will scene ID. We'll set the scene ID equals to true, and that's all we need to do. Text next ID has been written. Let's run it for once. It is giving us okay result. Okay. Last thing we need to check is one major thing. There was a edge case. Time drift edge case. If time drift is less than 5 seconds, we tolerate it and we set it to the last timestamp. But if the time drift was greater, we waited for the time drift to settle. So that's the functionality I will be testing now, and this will be our last test for this package. Okay, So what we will name the test is test uh, clock drift, because clock can drift in server environments. That's what we are testing. Um, T star testing dot p. Looking at this, I think later we will also write some benchmark test. P dot run. But for now, our main focus is normal testing. Small clock drift. If there is a small clock drift, whatever function does, and if there is bigger clock drift, whatever function does, that's we are testing. So what it will do is, now we will take the now time, which is currently, okay, and s dot last step. Oh, sorry, we don't have the s. Uh, we don't have s in this function, so I'll write s equals to new with id bar. S dot last temp equals to, if we will set s dot last temp to now plus, let's say we tolerate up to 5 ms of drift. So let's say 2 ms drift. So last time step is ahead of the current time step, uh, which means we are somewhat behind. Okay. So what will our function do is, we had to check this. So we'll generate ID s dot next ID. We have ID. Um, Now, as we have defined, if the drift was small, it will use the last timestamp. Okay. So what I will do is, I'll take out the last timestamp from the bits. How I will do that is by this. I'll take the ID time equals to the ID generated. Left shift the timestamp shift, which is this sequence bits plus machine bits. So we have now only time bits, and we will add the epoch value we have. So we got the time in our according to our we got the time in Unix milli. Okay. If id dot id time, if id time um, is less than s dot last step, id time should be greater than or equal to the s dot last step. So we will do is, we will throw error p dot error expected id time to be greater than equal to last step. So we expected the id time to be greater than or equal to last step uh, during small drift. Small drift. Okay. Got percent p less than percent p. So we got id time less than over s dot last step. Okay, let's format this out. What the heck? Okay. Next thing we will do is, we will test for larger clock drift. Larger clock drift function will be like our New, we don't need it. We will have a now, and we'll create a larger clock drift. Let's say a larger clock drift of 10 milliseconds. If there is a larger clock drift, what we will do is we will wait for the timestamp to be equal to our current stamp, uh, to be equal to our last stamp to be equal to our now stamp. So let's write about that. So we'll have a start read time dot now. I'll generate a ID. Next ID, and elapsed time will be time dot since start. We will check how much time has been elapsed. So it should have waited at least 10 milliseconds, 10 milliseconds or more. So what we'll do is if elapsed is less than 10 into time dot millisecond. If it hasn't waited about 10 milliseconds, we'll throw um, we will log this one and generate a warning like warning large clock drift rating was short. We'll have percent to be here. And what can be the reason for this? There can be a reason. Sometimes there can be fast execution or scheduling. Might be uh, due to fast execution or scheduling. Sometimes we can't do anything, so we just write this like this. And next thing what I'll do is I'll have ID time just like we did above in the last function. Uh, I will check the same thing like this. I'll have ID time generated like this. If ID time is less than last step, the last step is 10 milliseconds ahead. If it is less than, then expected this to be greater than during, after waiting. After waiting, you got percent %d less than percent %d, and I think all the tests have been done for this part. I haven't run this one. Let's run this. Run pass, 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 pass. Oh, it's a pass. Let's run this once and for all in a terminal. So what I'll do is clear the terminal first. Then I'll write to test /web.top. All the tests for our yeah, this is a package, Snowflake package. The test result was okay, and that's all we need. Next is our testing for retry engine. What I'll do is I'll write tests for this. First, let's format it if it hasn't been formatted, and let's start the testing for this. So it will have for this there will be two functions that don't need any external support, but the handle failure function needs mocking of the store and the queue. So let me write this in quick bits. first is the function we have in retry engine, which is should retry. Where is it? This is here. It retries if retry count is less than max retries. So we will have some test cases and test it against them. So let me write the tests. Retry underscore test. Go. So what we do is test. We'll have a test function for test and import testing. Okay, we'll have test should retry. We'll test this functionality first. So for this, what I will do is I will have some test cases with what we want the result to be and what are the test cases. So let me write the test cases equals to it will be a struct array. Why it will be a struct array? Because job is a struct, and it will have some fields of job, which is name, string, um, name for the test name, and a job, which is job.job type, and lastly want, which is food. Okay, so we'll have this, and what is the issue? We'll have cases like this. Pretty call of cases as this. So first case will be our um, name. Name of the first case should be should retry when um, retry when retry count is less than max retry count is less than max. Okay, the name is this job. We have to create a job, and this is job, which will be retry count equals to 0 and max retries equals to 3. What's 3? And want we want true. So this should succeed. Next thing we need is name should not retry when retry count equals max retries. Here you have a job like this. Job will be retry count will be 3 and max retry is 3 want false. It should not retry. Okay, retry count has been already reached. And last, if retry count has already exceeded, we'll need a case for that too. Should not retry when retry count exceeds max retry. So I'll have retry count as 4, want equals to false. Now our cases for the test are done. What we'll do is we'll range over this for this test case in our range of test cases. We will have test cases t.run. Name is name, test case dot name. Function will be our one like this, and if we will have if got we will run the function here, should retry to the job as test case dot job, and we'll get a boolean dot not equals to dot not equals to j dot sorry test case dot what. If got not equals to what, um, then we will have simple as this t dot f, which is should retry equals to percent we want percent v. We will have got test case dot so it will check each of the test case one by one, looping through it, and let's see the test. It gives us a okay result. Nice. Next thing we need to do is we will text the next delay function. You remember the next delay function counts the next delay using base delay into exponential of retry count plus a random jitter. A random jitter ranges from 0.04 of the delay. Okay, so let's write functionality to test it. So it will be a single function func test next delay. So let's have a test. Testing dot let's create engine. We have to create a new retry engine which has a max delay of let's say 10 into 10 seconds time dot second. Let's have a max delay of 10 seconds. We'll create a job j equals to percent job dot job having values of delay as initially 1 second time dot second. Okay, initially 1 second and retry count equals to 1. So it has 1 second delay and retry count is 1. So what I'll do next is I'll have delay equals to next engine dot next video with our job past here undefined j. So sorry, this one like this. I have a delay. Now what I will check is, let me write the thing. I think you can better understand. I'll check if the delay ranges from the base delay to the exponential of that plus jitter. So let me write it. Check if delay is at least the exponential backoff, which is our in this case, which will be 2 raised to power 1, which will be 2 seconds in this case, and within jitter range. The jitter range is 0 to 0.4. So 0.4 of our delay. So that will be up to 2 seconds plus 0.4 into 2, that is up to 2.8 seconds can have a delay. Okay, we can have a delay. That's right. So let's write about this. If we have a delay or less, if delay is less than 2 seconds, sorry, 2 into time the second, or delay is greater than 2800 milliseconds, because that is 2.8 seconds. Time dot millisecond. Then we will throw error. The error will be t dot error f. Next delay equals to percent we want range inclusive of 2 seconds to 2.8 seconds, and our next delay we got is delay. Nice. Next thing we will check is if we will check if max delay is capped at around 10 seconds currently. So if we pass a delay greater than the max delay, will that affect, how will that affect it? In a function, if we pass it, it takes the delay as max delay and adds some random data. What is this? If statement can be modernized using index. Minimum j dot delay. Okay, let's have it this way. No issues. Okay. So we will check delay, check if delay greater than max delay. What it should do is it should get back to 10, which is our max delay, and have some random jitter detect, and the range should be around 10 to 0.4 of 10 is 4 and 10 to 14 seconds. Okay, so let's create a j.retry count. We have to change it. Let's create it to no issues. We will create it to 10 because our what we call it, our jitter value depends on this the retry counts. Sorry, delay value depends on this. With 10, it will be 1024 seconds, and 1024 seconds is approximately 17 minutes, which is much higher than our anticipated max delay. So let's write it. 2 raised to 10 equals to 1024 seconds. Okay. We'll calculate the delay. Equals to engine dot next delay. We have created a delay. We need to pass the job here. Also, I think later I will change the functionality of this. So that we can have much higher delays. But if a stagnant job happens, like if a job that demands a delay of around 2 days, that will be too big for our system, and if hundreds of that jobs comes, that will block the system. So I will not likely call this. I'll check what we can do about this, but for now this is our good approach, having a max delay set, and max delay I think can be configured if using EMP. Yep, max delay can be configured, so the user is responsible for setting max delay, so I don't care about this. 10 into time dot. It should be ranging from 10 to 14, or delay is greater than 14 into time dot second. If either of those happens, then we will generate an error, which will be next delay is equal to this kept at next result equals to our percent we here. We want range, in range. We want the next delay to be in range 10 to 14. 10 seconds to 14 seconds. And we pass on the delay here. That's all we need for our this test. We'll run the test. One thing I need to test here is coverage. Let's test if this covers all the PD, previous application, Snowflake, and go test dash coverage. What was that? What was that? Oh, sorry, this was not the flag. The flag is covered. Yep. 100% of the statements are covered. And in this, we don't have test. We haven't tested the what we call it. The handle failure function. So for that, I'll think I will. Should I write it now? Should I write it later? For the handle failure function, I have to write mock store, mock queue, and all that, and it will be around a big chunk of code, around 100 to 150 lines. So I'm thinking I'll postpone the handle failure part to tomorrow, and after that, I will take one of the jobs need Redis integration test here too. DLQ also need the Redis integration test, so I'll need a Redis integration test. And handler does it need any testing? New registry, it will be a small test file. Okay, so I'll see what I'll do in tomorrow's testing. But for today, let's leave the stream here. Okay, bye. Thanks for watching.